first, any question from last lecture? So I put an iClicker question. So if you are in the room, you should answer the iClicker question. This is based, so one way to solve this problem is using Ampere's law. Which is, are we good? Any question? People at the back? So Ampere's, what is Ampere's law? So basically, if you have, if you sum the parallel component with respect to path over a closed loop, it's equal to the mu naught times the net current inside the loop. Okay. So to do that, let's say for this problem, this is a simpler version than the one that we did in previous iClicker. So in this region, if you make, well, you cannot see my cursor. In this region, if you have this loop, then the amount of current is I. Okay. And then in this region, the I enclosed is I. This one is also I, but the I enclosed is not the magnitude, but the net. So this one, if this is your loop, then the I enclosed here is equal to I minus I. Right? So we have done this twice in the class. So you know what that means. That means it may be in exam 2. Any question? So I'll just put, yeah. 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 I don't know how to, I'll grade this after the class. I'm curious how much people know this, and this is not, as long as you answer, you give a full credit. So can you point the birthday of Einstein on that iClicker? I mentioned that in class. I'm just curious how many people pay attention. If you're not sure, just put number. Just put, just touch the screen. It's actually not bad. All right, so what is his birthday? His birthday is March 14th, 1879. I know this calendar is not 1879. So that's, are you guys good? So I practiced last night, and I did this with my daughter, and he said, your class will be dead silent because they think that the bridging is really rough. Anyway, that's all I have, so I'm gonna do that. So this is my birthday, March 13th, 1979, okay? So you may guess that I wish I were born a little bit later, right? So I wish I were born, guess what? Because I can use ChatGPT to prepare my lecture. So this is my bridging towards discussing ChatGPT. My daughter hates this bridging. So ChatGPT, we are still learning about ChatGPT. If you use ChatGPT in Perusal, some of your classmates are really good in flagging those comments because apparently you can check that. Anytime your friends flag those comments, you actually don't get credits. So either you paraphrase it or you declare it. The answer below, the comment below is generated by ChatGPT. Then at least that way your friends will not flag your comments on Perusal. So every time somebody flag your comments, you get 0 credit. And even worse, some people actually copy and paste comments from other person. Some of you copy and paste your own comments, and I unflag that. But if you copy and paste other students' comments, you don't get credit, so you're wasting your time. Some people comments the page number, that doesn't count towards any point, so don't waste your time. Okay. But if you ask me, the fact that you highlight the page number is better than if you don't open the textbook. So that's the bridging. I have another bridging for you. I have a lot. None of them is good. So another one is Einstein was born on the March 14th. Another scientist that many people admire is Michael Faraday. We started our lecture on Monday by discussing Michael Faraday's contribution, but the lecture actually finished at Ampere's law. So we will finally do what he delivered to humanity. So we discussed that Ørsted started or did his famous experiment in 1820, and then it took people. So I'm not going to continue until everyone at least does your best in respecting other students. Okay. Good. So it took Faraday more than 10 years of working in the lab, and I can show you what he did. He did many things. So first, maybe briefly, Faraday was born in a poor family. He had many breaks, maybe 3 breaks at least. One is when he was 12 or 13. He was given apprenticeship in bookbinding company or a printing shop, and he did a good job. So he was the doormat of the business, but if he did a good job, people actually do notice. So if you email professor, hey, can I volunteer in your lab? If you work hard, actually professors pay attention to that, and we'll do our best to help you. And then because he did really well, one of his customers invited him to go to Royal Institution, where he learned physics, and then he saw lectures by the most famous chemist at the time, which is Sir Humphrey Davy. And then so at the time, you cannot just volunteer. Like at one point, a few high school students volunteered in my lab. At the time, if you want to work in a lab, you have to graduate from either Oxford, Cambridge, or maybe University of Edinburgh. But he didn't have formal education. He learned by himself, and he made many significant contributions to physics. One of them is the one that I'm about to show you. We have discussed his other work, which is DC motor. DC motor actually was invented by Faraday. So Elon Musk chose the wrong scientist as the name of the company, but that's not the reason why I cannot get Cybertruck. All right, so the experiment is really simple. Ørsted showed that a wire with current can generate electric field, and that thing alone was bizarre, because at the time, people think that energy can only travel along a material. So the fact that if you have wire, there is magnetic field in vacuum, that thing was a breakthrough. And then people tried to see whether we can go the opposite direction from magnetic field. So I have this magnet, this is north and south. It's connected to a coil. And this is basically an ammeter or galvanometer. So, let me zoom. So, zoom. All right, so the experiment is really simple. If you just bring a magnet close to a coil, you don't see anything. So people spend more than 10 years in this experiment. They put magnets here and there, and maybe when the needle moved, they thought that because they tapped the table, But what Faraday noticed is that when there is a change of flux, there is current. So this is like really magical. For us, it's really normal because we have benefit from this phenomena for so many years. This is the basis of our electrical civilization. But in the past, this is like amazing science, and Faraday, that's why Faraday was a rock star, basically. All right. So that's the experiment. But when we discuss electromagnetic, so this is the experiment, is shown in your textbook. But when we discuss it, there is a standard way to teach electromagnetic induction using blue. Okay, so let's say you have this magnetic field, okay? And I'm gonna give hints. Always. And you have this loop. And I'm gonna give you a hint. I connected, so this one is light bulb. So this is a really long rail, and there is a movable bar here. Okay, so there is no battery. That's one thing. So the question is, what happened? So all of these are B. What happened when we move this bar? So this bar can move left and right. So what happened? From your perusal. This is a perusal of previous lecture, Monday. So what happened if we move this bar? Anyone wants to guess? First, what happened with this light bulb? There is a reason why I drew a light bulb, right? This is how some people do exam. They try to see as many hints that I put. There is a reason why I drew, yeah, Sophia. Oh, the light, it's a good guess. This one, let's say this one goes to the edge of the universe. So as long as you move the bar, like what Sophia said, the light bulb will turn on. Okay. Anyone still remember from perusal? Nope. Okay. So this is because this part of the experiment is the area. Okay. And the magnetic field is constant. If you move the bar to the right, then the area increases. And we discussed it earlier in the context of electrostatic. That means the flux. So in electrostatic, we define flux, which is phi, is equal to the field times area. In this case, B times A. But here, there is angle, which is cosine phi. Sorry, what is the flux? So I inherit the symbols from your textbooks. There is a small phi here. I'm just going to draw it like that. That's small phi. Okay. So the flux is equal to field times area. The field can be a field of hydrodynamic motion or electrostatic field or electric field. In this case, B times cosine phi. Phi again is defined as the angle between the line that is perpendicular from the surface. We call that a normal vector with the vector fields. Okay. So in this case, in this example, is equal to constant 90 degree. Sorry, 0 degree is equal to 1. Right? In this example, flux is equal to B times A. Okay. And then next is the flux constant when after we move the bar at constant speed, is the flux does the flux stay constant? Eva. Sorry, good. Andy, anyway. He's busy. He's doing more important thing. Okay, thank you. Anything else that I forgot to do? So so flux is equal to B times A. Next, does the flux constant? After we move this bar at a constant speed, does the flux change or stays the same? When we move the bar, first, does the area change? The area change. So the area change, that means this one change, or I don't know, increases. Therefore, if as long as B is constant, then the flux is also increases in this example. So consequently, what happened as we have seen here, when the flux change, in this case, the field changes, but the area stays the same, as you can see. So one thing that you will learn in a few slides is that there is EMF. This is E, electromotive force or voltage, is equal to minus. Don't worry about the minus sign. You can put it inside an absolute sign. That's fine. Times the change of flux. Okay, and you can put N if you want. So this is the change of flux. Okay, but that's yeah, that's here. Sorry, I missed one thing. The change for a given over time. So there is delta T. So that means the fastest we move the, or in this demo, the slowest I move the, wait, I broke the galvanometer. Oh, I did it too fast, sorry. So I did the demo too fast. But if I move the magnetic field slower, I will get less currents. So here, by moving the bar also generate a current that points counterclockwise, and we will discuss about the direction of the current later. Okay. Any question? Yes, Sophia. Yeah, it's the same thing, but the current will point towards different direction, and soon enough you cannot move past this light bulb. Good question. Any other question? Is that, do you have any concern about this example? People at the back. Is that concern? Yeah, Holden. We will discuss about the currents when we discuss about Lenz's law, which I plan to finish today. Okay. Thank you, but keep that question for, I don't know, 20 minutes. So first, in the beginning of the class, I told you that the magnetic forces don't do any work. Is that still the case here? Work is defined as force times displacement times cosine theta. So because this is a loop, then if you sum all the work, you get 0. So that's not an issue. And then every year, there is always a student that come up with a valid criticism. Like, why do you teach us magnetic fields? It doesn't do any work. It's useless. Why this thing is useful? Why magnetic force in this context is useful? maybe this is philosophical question, not physics question, but I find it useful. So you can be very strong. You can go to the gym twice a day, but you cannot move electrons. So only because of magnetic fields, you can move the bar, you can use your muscle and move the bar, and you can also push an electron, and you get something useful out of it, like an AC generator. Good. Any question before we do iClicker? Let's do this iClicker, and I will grade this question after the class. So be careful with this cosine phi. That's the angle between the vector that is normal or perpendicular from the surface. But the question is asking you about the plane of the area. So the question is, a flat coil is in a uniform magnetic field. The magnetic flux phi through the coil is greatest when the plane of its area is, right, let's spend 20 seconds. Let me give you. So 5 seconds. 3, 2, 1. All right. So this is a picture from a figure from your textbook. Be careful with the choice. This is their choice, not mine. The flux is the capital phi or phi if you are Greek, and the small phi or phi is the angle between two vectors. Okay. So this is the answer, where the plane is perpendicular, but the normal vector is parallel. So see, where the field, the plane is perpendicular. So good. So 3/4 of the class get it right. Okay. This problem is fairly straightforward, and maybe we can skip this problem. Is that okay? Yeah. So basically, you just need to use this equation: B times A times cosine phi. And this question basically one of the points of this question is testing you whether you understand the SI unit. But I'm not a big fan of asking students about the unit, so I changed the unit to Weber. But anyway, the answer is, as far as I remember, is C. All right. So back to the theory. So there are different ways to change the flux. Okay. In this case, we change the area from small area to bigger area. Small area, bigger area. And what is the difference? Meaning like the area difference is this area here. Okay. So that's one. Another way to change the flux is by moving the magnetic field. Oh, works now. Yeah. So you can either change B or change the area. So in this example, your book gives an example of somebody change the area of a loop. Yeah, change the circumference is the same, but the area is different. The area is actually smaller, but the circumference is the same. This is an example from your textbook. Do you want to do this question? Let's do this question. Okay, let's spend 2 minutes. So basically here, the thing that changed is the magnetic field. So the question is, the magnetic field in the region between the poles of the electromagnet is uniform at any time. Still, it increasing at the rate of increasing delta flux divided by delta T at the rate of 0.020 Tesla per second. The area of the conducting loop, which is here, I cannot point here, is 120 centimeters square, and the total circuit resistance, including the meter, is 5 ohm. The first question, find the magnitude of the induced EMF in the circuit. And this one is number. Okay, so you can spend 2 minutes. Basically, you need to use this equation. And because it is not a coil, you can say N is equal to 1. Be careful with the unit. Tesla is an SI unit of magnetic field. But for the area, the SI unit is meter square. So this is the conversion that you need to use. And this one should not be part of the cheat sheet. Cannot say this. So in case you're not sure, the thing that changed, so delta flux divided by delta T is equal to here, because the area stays the same. Because the change of flux is basically the change of magnetic fields times the area. Oh man. Can I? Thank you. All right. So 10 more seconds. 5, 3, 2, 1. Okay. Can we? Sorry, I'll grade later. So this one, the change of the magnetic field is 0.02 Tesla divided by second. And the area is, thank you. The area is 0.012 meters square. Okay. So that's this part of the equation, and N is equal to 1 because it's not a coil like this coil here. Okay. So if you put the number, you get 2.4 times 10 to the 4th volts. The reason why I know the unit is volt because everything is SI. And if you want to multiply by 1, you can. Any question? Yeah, Gabe. Okay. Yeah. So I can. So next time, so I can delete. Okay, since we will delete the iClicker, there is a second part of the iClicker. So next, when you put the answer, don't put the unit. Okay? Just put the unit in SI. Yeah. Yeah. Yeah, it's negative. But what we care right now is the EMF. EMF, typically we do it in, it's like the height. One can come up with convention that height should be negative, but most people, it's, I hate to say this, but it's like common sense thing. Once you know, once you grow up, you know that height is positive. Here, unfortunately, like physicists, engineers, we use positive volts. So this is why here we put absolute value. Okay. So there is a second part of the equation or question, which is we know that the resistance is 5 ohm. The question is, which is question B, find the magnitudes of the induced currents in the circuit. Okay. And you have, the reason why I use numeric, because some of the questions on the exam is numeric. No multiple choice. Some of them. Some multiple choice, some numeric. Okay. Let's spend a minute if we can. Probably we have to spend 2 minutes. So what is the current here? So you should know if you have a resistor or a resistance and you have EMF somewhere, then you can calculate the current, right? So 5 ohm. And the answer that you put is in SI. You don't need to put the unit. All right, 30 more seconds. Fifteen seconds. 5, 3, 2, 1. Okay, so what is the answer? So there is a formula that we use, which is V is equal to, so I call it R times I is equal to V, but your textbook used this formula, so I respect that. So V is basically I, so V is the EMF. Sorry, sometimes I just cannot speak English. So I is equal to the EMF divided by R, right? And the EMF is equal to 2.4 times 10 to the minus 4 volts. And R is 5 ohm. The units are in SI. So this is, I just gonna multiply by 2 and lower this by 10. 10 divided by 2 is equal to 5, basically. So 4.8 times 10 to the minus 5th amps. Okay. Is that correct? And some of you may answer in milliamps. Well, the question asks you to provide the answer in SI, which is amp, not milliamp. Okay. So this is basically what we did so far, which is magnetic flux is B times A times the angle between the normal vector and the field lines. Be careful with the capital phi and the small phi or phi. And then the equation for the EMF is minus n. There is minus sign here times n times the change of the flux, which is given here. N for now, n is 1, but soon we will do, we call it basically inductors. Inductors is a coil. So in that case, there are n loops per unit per unit length. So n can be more than 1. And that thing is the electromotive force. Okay. Any question? Now we will go back to Holden's question, which is what is this negative sign here, or where is the direction of the current? And your perusal spent a lot of time discussing about Lenz's law. Okay. So Lenz's law is named after Heinrich Lenz. Basically, nature doesn't like a sudden change. Okay? So if the flux increase, if the flux of the magnet increase in this loop, or let's use this example. There is no laser pointer here, but let's use this example. Yeah, so we have a loop and we have a bar magnet, and if the bar magnet move to the right, so what happened is that because the flux changes and the loop and the flux increases, the induced current will produce magnetic field that oppose the direction of the loop. Oh, sorry, that oppose the direction of the magnetic field. So back to this example, because the flux points away from you like this, right? The field, the induced current will produce current that generates magnetic fields that oppose the external magnetic field because the flux increases. So because the flux points towards the whiteboard, then the current will produce magnetic field that points from the whiteboard to you. So this is why the direction looks like this. Okay. And similarly, if we, like Sophia wants to move the bar to the left, then the flux decreases. So what happened is that the induced current would like to oppose the change and produce the magnetic field that is the same as the previous magnetic field or magnetic flux. That's from your perusal. Is that clear? Maybe with practice. So let's use this example. So we have this example, and maybe we don't do iClicker. The magnets move to the right, so the distance between the loop and the bar magnet is closer. That means the flux increases. Okay. So for this question, what is the answer for the iClicker question? Does moving the bar magnet closer to the loop increase or decrease the magnetic flux? Sorry. Okay, what is the answer to this question? The answer is it increases the magnetic flux. Right? So the answer is A. So as I mentioned before, if the magnetic flux increase, the induced magnetic field or the induced current will produce induced will produce magnetic field that oppose the change. So the magnetic field due to the increase of flux will point like this. Okay. So there are many layers of this. You need to pay attention. If you're checking important messages, maybe you can wait for like a few minutes until after the class. Yeah, hold it. Yeah, yeah. It try to oppose. It depends. Most likely it will not cancel, but it just reduce the change. Okay, since the induced magnetic field, since the loop wants to make that magnetic field in, I guess, crimson or maroon, then the induced current will follow right-hand rule, basically. So what we have discussed is this configuration here, where the bar magnets move towards a loop. But one can also move the bar magnet away from the loop, and you get the opposite induced current. This is from your perusal. Any question? And there are some example problems that I will include in the lecture notes that I send you, that I will send, that I will upload later today. So I want to take some time because I've been asking our team to prepare demo, and most of the time I didn't have time to do the demo. Do you guys want to do the demo, or do you want to do the demo in the lab yourself? Okay. But first, this one, okay, Lenz's law. Many students have problem with Lenz's law and Kirchhoff's law. Lenz's law is part of exam 3. Kirchhoff's law is part of exam 2. The best way to do it is by doing a lot of practice problems. Okay. Like anything less, like any other skills. Okay. So Lenz's law is very useful. One, you can have a lot of fun. The nice thing with this job is I get a chance to play with many toys like coils. So one is, Andy, can you please help me? You're the DJ, you're the cameraman. Oh, sorry. Just zoom until basically the students should be able to see the demo. Right now it's probably like this. Okay. So this is a coil. So N is more than 1. And this is a magnetic field. I assume red is north, white is south. The poles, the exact poles, they don't really matter. So what this thing does is if I move the coil, that means B increases, the area stays the same. The magnetic field increases and the magnetic flux also increases. So what happened is what? It will generate currents on this loop, right? And then this loop is connected to, if you follow this cable, it's connected to this loop here. So we can do, so in a sense they communicate, but there is no battery. So what happened if I increase the loop? I can oscillate, or I can move the other loop by changing the flux in this coil. So this one shows that you can send communication, either that thing is in the form of telephone, like old school telephone, or something else using inductance. Another thing that is useful if you have electric car or electric skateboard is you can stop a motor, or you can stop movement. So this is just a pendulum, and I will tell you what this pendulum is, but I want you to get a sense of the oscillation. Good job, Andy. So this is the oscillation, and then I'm gonna change it. So it's the same thing. This is metal. It's not magnetic. So and this is very strong magnet. It's 4.5 kilogauss. And aluminum is not magnetic. If it's magnetic, then it will stick. It will stick like this, right? So I'm gonna change this pendulum with a different pendulum. So the difference between the previous one and this one is that this pendulum doesn't have slots, which means that electric current can travel in circles. So every time we have demo in class, I can always ask demo question about demo on the exam. Just part of evaluation. So remember, with the one with slots, the movement is not hindered by the strong magnet. But let's see what happens if a metal without slot move into the magnet. So there is what we call here is electromagnetic braking. So what it does is, because the magnetic flux increases, so right now the magnetic flux on this plate is 0, and then when it hits the magnet, the flux increases, and because of that, there is braking, or the movement is slowed down. Does it make sense? Can somebody explain this experiment? How about you? Yeah. Okay. So based on Faraday, if we have change of flux, we will get currents. And aluminum is not a good conductor. So if we have currents and resistance, we get heat. The only energy that I put to this pendulum is mechanical energy, or like gravitational potential energy, or mechanical energy. Since the system emit heat, it must cause energy. And since the only source of the energy is mechanical energy, then the mechanical energy has to decrease. Okay. You can even, when you put your hand here, you can even feel the resistance. Any questions? So we still have 3 minutes. Last is we will do the opposite. So if you are curious, I can return the pendulum back to the original. And what you will see is that the movement is not affected by the magnetic field. All right, so I have 2 minutes. Next is again, nature doesn't like sudden change. So when this aluminum, again, this is not magnetic. When I add a strong magnetic field to this aluminum ring, it will generate induced current, like what we discussed there. And this induced current will generate magnetic field that will oppose the magnetic field of this coil, and this one will jump. Okay? So you can use induced current either to slow down a motor or for movement. Okay? So this one, so that's something like that. And you can even use it for something useful. For example, you can turn on a light. And this is a nice ring that Seth prepared. This one has a slot, okay? Which means the electric current cannot circulate. So if I use this ring, what do you expect? It doesn't go. And we have bigger ring. And finally, I have this Seth put this ring in a liquid nitrogen. So what happened if we cool down a ring or a magnet, not a ring, a conductor? What decreases other than the temperature? The resistivity decreases. So what happened when the resistivity decreases? The current will be larger, and we expect that this one should travel higher. You want to catch it? Don't do it like this, right? We have helmet if you want to do that. But, all right, that's my best game of the day. See you on Friday. Thank you. You came at the right time.